We have Evan Smits, who's going to run the webinar really for us and introduce the solution to everybody who's attending. Just a bit of introduction. So we work for Qfunsoft. We're the sole suppliers of simulation software in Southern Africa and Africa. And myself I'm Laura Van Niekerk, and I've been with the company for over 10 years now. And we've got one of our senior application engineers, Dr. Evan Smits, who will be really in charge and telling you more about how you can make best use of this solution based on the challenges that you will have within your company. So Evan, over to you. Thanks a lot. And please ask questions in between the attendees. We will have questions at the end as well. But as we go on, if there's anything you want to ask, please ask and we can address it then. Thanks a lot. Over to you, Evan.
Well, thanks, Lauren. Thanks for the introduction. I'm just going to actually turn off my camera during the chat and then or during the talk, and then I'll turn it on as we go. Right, so what I wanted to focus on with the webinar today is looking not only just at Sherlock, but also how we can integrate Sherlock with other Ansys products and really sort of extend the power of what Sherlock can do for electronics reliability. So we'll kick off today with a little bit of an introduction just about Qfunsoft for those who maybe don't know us that well. And then we'll start looking at what Ansys can offer in terms of electronics reliability, particularly what Sherlock is for those who maybe don't know much about it. And then we'll look at how we can take Sherlock, link it with other Ansys products, and really get a much more powerful analysis from that. So firstly off, Qfunsoft, we consider ourselves the leading CAE software provider for the sort of Southern African region. We've been around for more than 25 years now, and we offer a range of services, focusing mostly on the Ansys suite of products. But we do also offer all the sort of support around that, so training of using the software, as well as the post-sales support. And we also do a bit of design and simulation consulting for those clients who maybe need that service in addition or instead of actually purchasing the software. And importantly, we also now focusing more than just inside South Africa. We're looking outside, looking to the rest of Africa as a key growth area. And so we're looking to support new territories throughout the continent. So that's been an exciting area of growth for us. Then looking specifically now at Ansys and who Ansys is and what they represent, as they are sort of the major product that we offer and support. So Ansys is considered the #1 engineering software provider in the world. They are the biggest, and the reason for that is that they focus purely on simulation. Okay, they don't get sidetracked with lots of other products like some of the other companies do. All they do is focus on simulation. So they really put all their energy in it to developing the best-in-class software with the best features, the best newest technology, the easiest to use functions. And that's really kind of why they tend to stand out amongst their competitors. And also kind of a bit about the philosophy behind Ansys, and I think this kind of also applies today for the topic we're going to talk about today. You know, traditionally simulation's been seen as this thing that kind of comes in at the end of the design process, when it's just kind of the design's pretty much done and we just want to kind of wrap things up and move on. But we feel that that's often too late to bring simulation into the design process, because by then, you know, pretty much all the decisions have been done and everything's been finalized, and to try and make changes at that stage is very hard and difficult and very expensive, more importantly. So we feel like we can really bring simulation earlier on in the design process, right up to the concept phase, or here we call it ideation. So anything from the sort of concept phase right through into even the manufacturing processes, and the actual operation of the product. We start talking these days about digital twins. So there's a lot of emphasis on developing this software that we can use really throughout the full design cycle of this product that we're designing. And with that as well, it's more than just about looking at a single analysis in isolation. So typically, we consider simulation of just a structural component or just some sort of airflow, maybe even the electronics on its own, just the antenna or something just by itself. We can consider that. But these days, simulation is about more than that. We very rarely just have a structure. It's usually a structure with some thermal behavior or maybe some aerodynamic loading on it. Electronics also, we'll see thermal is a big part of that. So it's really about how do we link all these systems together. And this is really where Ansys kind of comes into their own and offers something very powerful, is that it's about how do we link these products together to get a much bigger or more detailed analysis of our system. Okay, and then it's also about how do we provide all the support systems around. So, it's not just looking at the system or the digital twin, but how do we look at this in terms of the bigger performance or mission of the components that we're looking at? How do we link it to different materials? Because that's also vitally important to our design. How do we optimize our design to make sure that it's better than we think it is? So it's about how do we incorporate all these different technologies and ideas and workflows together. And that's kind of what we're going to touch on some of these today in this presentation. So firstly, what do we think about with electronics reliability? Why do we want to put so much effort into this? So more and more sort of technologies and designs are incorporating some sort of electronic component in it. We're becoming very dependent on the connectivity of our components, sharing information, giving feedback to the customers or to us as the people who design the products. So it's really about, everything is bringing in some sort of electronic device these days. And also it's about like, how do we're shoving all these different technologies together. Things need to be smaller, they need to be faster, they're carrying higher currents. How do we deal with all these different sort of challenges that are kind of conflicting with each other? And traditionally, many people or many designers tend to use this sort of iterative approach. We build something, we break it, and we figure out why it broke, and then we start again. We redesign it, build it, test it till it breaks, and so on. But this is a terribly inefficient process. It takes very long, costs a lot of money. We have to build lots of prototypes, and it's also not always clear why something breaks. We see it breaks, but why? Like, what was the cause? And so, if we can look at a way to kind of streamline this basic process, add some more information, some more value at the different stages, maybe we can learn a bit more about why the component broke and how do we fix that and rectify that. And this is really where Ansys and simulation technology comes in, because we can use simulation as a tool as a sort of way to cut out a lot of this process, a lot of this iterative process. We do all the designs on the computer. We don't need to make as many prototypes. We don't need to, or when we do break them, we don't have to worry about why they broke. We can tell that from the software itself. Okay, and then this is where something like Ansys Sherlock comes in, and this is kind of the core sort of central focus today, is looking at electronics reliability and how do we go about predicting their life and why they break and if they are going to break. Okay, so Sherlock, what is it? It's a software that is based on physics of failure, and then it uses the underlying physics of the components to then predict and look ahead and say, well, how long is this component going to last? What happens if there are multiple things going on at the same time? Thermal effects, mechanical effects, all of this. What happens if we put all of these together? How does that actually affect the lifespan of our product? And So it becomes this tool in helping us design and predict our components. And we can then use this in various ways. So one of them is standards compliance. So, Ansys products don't necessarily, they're not necessarily tied to any particular standard, just because there's so many with many different requirements, but we can be used as a tool to meet these requirements. Okay, so we can use Sherlock to say, will our PCB actually meet the requirements of this standard? So we can interpret those standards and use Sherlock as a tool for that. Okay, and we'll see there's many other benefits to Sherlock as well. So one of the kind of the unique parts about Sherlock or features of Sherlock and how we can use it, it's not only an analysis tool, it's a very powerful pre and post processing. Okay, so we can bring in our ECAD components, our PCB model into Sherlock. We can turn it into fully fledged 3D model. We can do the analysis on it within Sherlock, and then we can take that analysis and make predictions about the reliability of the components and the time to failure of those components. So it's really kind of comes in at every stage. We don't necessarily need to link it to other products. It can do a lot of self-contained analyses within Sherlock, and we'll see how we can link the power of the pre and post processing to other Ansys products as well. Okay, so starting off with the pre-processing. So one of the really nice features of Sherlock is that it comes with a massive parts library built into it. I think now there's over 600,000 components, and that was, I think, a couple of years ago. So there's so many components that are built into Sherlock. So when we define our board, we design the layout, we know what components go there. We can actually place representations of the actual components we're going to use from the manufacturers with all the appropriate data. So what does the package look like? What is the size? What is its thermal properties? What are the materials it's made out of? All of those things that have a bearing on the reliability predictions can be extracted from our library. And the nice thing about the Sherlock library is they support this with a team of librarians, as they call them. So they're constantly adding and sort of extending the library of Sherlock. And as a customer, if we want to have something formally added to the library, we can actually put in a request to the librarian team, send that information to them, and then they can actually put that part in the library. And so we know it's there for next time we want to use it. So this is a really awesome sort of support service that comes with Sherlock that extends the workflow. Obviously, we can add our own components ourselves. We don't have to wait for the librarians. But if we wanted to be part of the formal release or the formal update, database updates, then we can do that as well. And just for those who maybe don't know, that the library does get updated sort of, let's call it every 2 months with further components and things like that. So there's always constant addition and maintenance of the part library. And then within the Sherlock framework, it obviously does the analyses and manages the different analyses as well, but then we can extract information from that. And this could be anything from looking at the lifetime predictions for each component. So we actually itemize out each component. And then we can also look at how the board, the PCB itself, kind of performs as a whole. So we can look at the distribution, the contour distribution of stresses and strains and displacements, and so on. And we can do that both in 2D and 3D and just see where are the problem areas in the board and what can I do to address them. Okay, and then ultimately the goal for Sherlock is to look at the cycles to failure, or how long is my board going to last till it potentially fails. Okay, because maybe just even one component failing could mean that the entire board itself fails. So we with all the different analyses we do, we build up this particular type of graph, a nice way to visualize it and say, well, okay, we've got all these different analyses. We've looked at the prediction of all of these, but what happens if we combine them? Okay, because obviously the board's going to experience all of these different environmental conditions, vibration, thermal cycling, and so on. What happens if we put them all together? Then we get an even worse or more conservative prediction of how long this PCB is going to last. And just to quickly highlight some of the different analyses that come with Sherlock. So one of the main ones is the thermal cycling. So here we can put in an environmental profile of the variation of the temperature that the board will experience. And then we can see what will happen to the components. So this could be anything from looking at simple solder joint fatigue, or we can do a full thermal mechanical stress strain plot for the entire PCB as a whole. We can then also do mechanical sort of tests as well, looking at things like shock, just an impact on the board, or of some sort of vibration coming either from random vibration or harmonic vibration. And we can see how that will structurally deflect the parts of or different areas of the PCB, and how that is going to then put strain onto the actual components themselves. And then again, we can then predict how long we expect them to last. And then we can also look at sort of manufacturing type tests, so things like in-circuit testing. This is also something that puts a lot of stress on the board. We might design it fine, but even break it during just sort of testing and verification. So we can simulate some of these processes, pick certain sort of impact points on the board, and see how that then influences the components as well. Okay, so there's a lot of different tests that are all handled within the Sherlock framework. You don't need to move around or know much about simulation background. You just define your PCB with all the components, and you can then just run these tests, and Sherlock manages it all for you. And all you need to do is view the lifetime prediction results. So some of the interesting use cases, that we can use Sherlock for, is that we can do some very quick what-if scenarios. So, for example, what if I change the size of my pad that gets soldered on, or where it's the component is soldered on? What if I change my package sizing? What if I change the PCB laminate design, maybe the thicknesses, or use a different material or something like that? This can all be done on the fly within Sherlock, because as much as you have your detailed ECAD model, your model of your PCB with all the different layers and traces and the positions of all the components, Sherlock does see it as kind of a flexible system where we can move these components around and make changes to a lot of these parameters and do what-if scenarios. So, for example, here we have some sort of mechanical shock test that we've done, maybe a drop test or an impact test or something like that. We find that there's quite an area of large strain or deflection in this area that's reducing the lifetime of our components. So here you can see it goes out the top of this little black box. That means that the component is actually going to fail. It's not meeting our lifetime goal of 10 years. It is failing before that. So now we can just take that component and move it around. So what happens if we move it here? Okay, it's obviously this is not tied to the underlying trace layout. So this is just more of what if, and then if it improves the scenario, we can then go and change the underlying board design. So we can also look at, maybe adding supports to move where the areas of high deflection are, because that, in this case here, this adding the support here in black, that would be sufficient to shift the area of high deflection away from the chip enough so that it meets our reliability goals. Alternatively, we could add in some sort of underfill material or some sort of potting material to glue that component in place. And you can see here that we have a virtually infinite lifetime there. This thing will never fail. So we can play around with all of these before we even go and make any sort of prototype or redesign it, and now need to book more time on the test bench and so on. we can do these analyses quite quickly and just play around with different ideas. For example, here, this is a case study we ran a couple of years ago using Sherlock. So the goal was to identify failure in certain components during a vibration test. So we then took the design, put it in Sherlock, and try to mimic the vibration test that they did. And we found that, well, straight off the bat, we did find failure. So that was obviously a concern, being a major component. We then compared that failure that we identified with the actual experimental test. So here's a photo of the components from that experimental test. And we saw the failure in these leads of the FPGA, and we could virtually one-to-one compare what broke, where did it break. So you can see here actually the actual leads, where it actually bends around the corner. That's exactly where we saw some cracking. So for me, this was probably one of the most sort of closest replications of what we could do with simulation and experimental data. And this then obviously brings in a great amount of confidence in Sherlock as a tool to predict failure within our electronic components. So then having that confidence, we can then go on and do further what-if studies, and we have really confidence that the changes we make will translate into the real-world improvements. Just out of interest, if you guys do want to see more about this case study, it is published on our Kufenstoff website, so you guys are welcome to go and have a look and read through that blog article there. So kind of summarizing this now about Sherlock, like trying to think, what is Sherlock and where does it fit in? So it's really should become part of the whole design workflow. When you're designing your PCB, it should really be worked with in tandem with Sherlock, because you can design the perfect board from an electronic point of view, but maybe from a mechanical structural point of view, it might have a lot of flaws in it that might need addressing. So we can use Sherlock as an initial design tool to help us look at initial part placement, maybe changing different components, maybe components that can handle the heat better, and so on. And so that can really sort of complement our traditional design process or ECAD design process. And so, yeah, it really kind of adds a lot of value if you can use it right early on in the design process. You know, you don't want to be making a prototype once your entire board is laid out and all the traces are designed and everything's being made, and realize, oh, the chips are not going to function as, or they're going to break within a few months of this thing operating. And so, to kind of just summarizing what we see now in terms of Sherlock and what value it can add, it's great at pre-processing. It's about building an accurate model of our PCB, bringing in the ECAD files or the different layers of the PCB, as well as all the components and what they have to offer. And then we can do a lot of really quick what-if studies and comparisons just to see how the board is going to operate, and if we can make any changes early on to sort of mitigate issues down the line. Okay, so that's kind of a nice overview of Sherlock and what it can offer. But today, what I really want to focus on or spend some time on is how we can sort of extend the capabilities of Sherlock and linking it to other Ansys products, because that's, you know, a lot of people who have Sherlock will have some other Ansys products, but it's also about how do we then add value to Sherlock and get really more detailed analyses of complex scenarios. All right, so when we think of Ansys and what it can offer, there's many different products in all different spheres of electronic systems. We can look at anything from sort of right down at the board level, the PCB performance, looking at signal integrity and power integrity. We could do things like EMI and EMC, and all of those can kind of a part of the reliability sort of analysis of electronics. But today we really want to talk about the actual thermal and mechanical reliability of the physical board structure. Okay, so that's kind of where we're going to concentrate today. And, you know, this slide kind of encapsulate how we can really link Sherlock to many different products here. So, you know, Sherlock can work very well as a pre-processing tool, but then how do we like bring in information into that to add value and to sort of make Sherlock that little bit more accurate and more relevant to the real world scenarios that our products will be going through. So we can bring in things like or you start off at a very basic electronic level, looking at things like power and signal integrity. That invariably feeds into a thermal model, because all the losses in the boards will sort of create some sort of heating effect in the board, so that we can take that temperature profile, bring that into Sherlock, and get a much more accurate temperature or thermal analysis of the components. We can then, from a mechanical side, shock and vibration, we can link that to our Ansys mechanical product. That is our flagship FEA, finite element analysis structural product. And we can then use that to kind of take the shock and vibration analysis of Sherlock to kind of another level. And then we can always, and you know, those analyses can kind of be done on their own in isolation, but ideally what we want to do is bring that all then back into Sherlock to get those reliability predictions. So it's all about kind of how do we link these all together and moving between the different products. So one of the first, or one of the bigger interesting roles that Sherlock can play in your workflow is by being a pre-processor. So this is where we can actually import the ECAD design into Sherlock, and then we can turn that into a 3D simulation ready model that we can then use for both the mechanical and the thermal analyses. So this could be anything from bringing in the actual PCB layers. We can either kind of lump them together into one sort of homogeneous board, if you will, or we can individualize and keep each layer separated as it's with its own unique material properties for a little bit more accuracy. But obviously that then adds a little bit of extra overhead in terms of calculation time. We can also include the actual trace mapping. So we can take our ECAD board from one of the ECAD tools, and we can actually then we discretize that board up, and we look at the distribution of the copper material, the traces, and the substrate material, and we can build up this sort of resolution sort of heat map here, and you can see where there's more copper in some areas than others, and that's going to affect the material properties of the board. Looking at things like thermal expansion and heat conduction and so on. Also, potentially heat generation will be different in some of those areas. And then we can also represent the traces quite simply as reinforcement. So these are like little reinforcing beam elements that we can represent in our 3D models as well. So, you know, we're not, when we're particularly in mechanical, we're not just looking at a lump of homogeneous PCB. It's actually got all these little lines of copper that actually add a little bit of stiffness and rigidity to the structure itself. So we can include those kind of effects, kind of very similar to this trace mapping concept. But we, instead of just lumping the materials together, we actually see each trace as a line element or beam element, for those of you familiar with mechanical. Or we can even go to the full 3D model where we actually look at each trace component as a full 3D geometry of material. That's obviously a lot more accurate, but now we need to mesh all these individual shapes and dimensions and all that kind of thing. And that just adds a lot of extra overhead, but it can be certainly for smaller components where there's a lot of detail. it certainly can be a viable approach. Okay, then also we can then look at other components or at the component level as well. So the previous slide was mostly just looking at the board level. Now thinking about how do we actually represent the components on top of the board. We can model them at varying different layers of detail. So we could obviously just have dead components, which are just literally a block and there's nothing interesting about them. Or we can even include the effect of, say, the leads, for example, and the shapes and positions of them. We can look at solder balls as well. Again, either simply representing them within Sherlock as sort of essentially a block, or we can go into, say, a full mechanical analysis and actually model the shape of them and look at the real local stress concentrations within those solder balls. You can do wire bonds, so the very little thin wires they're making electrical connections, take that into account, and so on. And so it's really about what level of detail do we want to include in our model, and where do we think we're going to get the most value. You know, do we need to model all the leads? Will that add some? Is that what's going to be important to us, or can we leave it out? So Sherlock is a nice way of, we can define all of our components, we can define the lead pattern within there, and then we can also choose whether to use them or not. So for example, when we export our model from Sherlock, so this would be a representation of our ECAD model within Sherlock with all the traces in green, all the copper traces, and then all the components in gray. We can export this to FEA, so it's simple as right-clicking and we go export FEA model, and then we can choose what level of detail we want. So do we want to include the parts? Do we want to include the leads on those parts? Are there heat sinks we need to worry about, and so on? So there's a lot of different levels of detail that we can include. And the nice thing is then Sherlock will go and automatically create a 3D FEA model for us. It uses all the information from our parts library from all these different components, and it can create, the life-size accurate components onto our PCB model for us. So we don't have to go and draw all of those components with all the leads and all the balls and all that. That is all done for us by Sherlock. And we can even choose to export it with a mesh or not. Or we can go and create our own mesh in mechanical or something like that if we really want to. So that's really a super easy way to go into the next stage of a multiphysics analysis. On the thermal side, if we want to do something, for example, with IcePack, where we want to take our PCB from Sherlock and go do a thermal analysis in IcePack, we can also then export to the electronics desktop as well. So again, just right-clicking and exporting. So this creates an EDB file format, which is Ansys's kind of internal file format that we can then, it basically turns the Sherlock representation of our model into the EDB format that then is read in by IcePack, and IcePack can create a full 3D model from that. So including all the trace data and all the components and all of that. So you're ready to work with that. So if you think of it like this, Sherlock can almost be or serve as a common source of geometry for both our thermal and our mechanical analyses, because we can take our ECAD model, create or set it up within Sherlock, and we can then export to both either a mechanical or a thermal analysis in different products. So this is also it's a really great way or great reason to serve as a pre-processing tool. Then looking at how do we actually model with these other products as well. So looking at on the thermal side specifically, we're looking at typically we're going to work with IcePack. That's why I've kind of highlighted it here. The idea is that IcePack is a simulation package for electronic cooling, and it's really focused about electronic products. So it works within the electronics desktop environment. We can do our PCB level analysis. We can do things like our DC power drop analysis and all of that, take it into IcePack, and we can get a very detailed sort of cooling model. So it's got a lot of built-in functions to put in, like cooling fans and all sorts of things like that. So it's a really nice way to do a thermal analysis and see, well, am I going to get sufficient cooling to all my electronic components? Here on this slide, we're just highlighting how we can, within the electronics environment, we can do a DC power drop analysis. So we can actually look at the power drop in a specific trace, actually see where all the hot spots are, where that power is going to be generated more intensely. And then we can take that into IcePack and get a very unique temperature distribution for that specific PCB. And then we can see if we can get sufficient cooling from that, where we position the fans and the casing and other vents and things like that. So once we have our thermal analysis, we can then bring this over into Sherlock. So typically the way to do it is through our sort of a contour map here of temperature. So we bring that in and we map that into Sherlock to get the temperature distribution across the PCB. So if we look at a particular example here, just a very simple example. So typically, if we want to look at a solder joint fatigue model, for example, these are the typical components that we need to put in there. So we obviously need to define our PCB with the parts. We put in our lifecycle goals, specify all the solder properties of the different components. And then the important thing is we need to specify some sort of thermal event, okay? And this can come from various sources. So one of them is a simple thermal map. So it's essentially just a CSV file. It's a list of temperatures of different components. So each component will get specified its own temperature, which kind of works, and that's very nice and simple. But what happens in between? So this is where we can bring in something like a thermal image, either from a thermal camera or some sort of simulation product, and we can then map those temperatures across. Or we can just assume the very basic profile. So this is a basic profile that we could put into Sherlock, and we just give it a minimum, maximum temperature, and it just assumes that temperature is the same for all components on the PCB. So those are the kind of three options we have there. To highlight the thermal map, how do we import that? So what we do is either it could come from a thermal camera, like we saw on the previous slide, or it could just be a screenshot from something like IcePack, or even an Ansys Mechanical. Maybe you've done some analysis there. It's just purely conduction and heat thermal analysis, and you get your temperature distribution from there. All we do is we take our image. You can see we've got a blue box and a red box here. The red box gets linked to the legend, the temperature range. The blue box gets linked to the outline of our PCB. And then Sherlock can then interpret that and map that to our PCB. So you can see here it's taken that thermal profile and mapped it to the outline of our PCB. And we can see that the hotspots do correspond to our main components. So here we can see that we've mapped it fairly correctly there. And what we can also then do is link different profiles. So as much as these look very similar, these two profiles, if we have a look at the maximum temperatures here, the top one does have maximum temperature of about 44 degrees Celsius, and the bottom one's about 99 degrees. So we can actually link those to different parts of the profile. So we can say, well, what happens at the lowest part of our thermal profile? We actually have this distribution at the top. And then when we get to our maximum profile, this is distribution at the bottom is what applies. So we could actually give Sherlock this kind of really detailed information as to what are the two extremes that my board operates at, and maybe some components get hotter than others under different conditions. And so we can therefore account for that difference in temperature. All right, and then if we turn that into reliability prediction, so if we look here at option 1, so this is where we imported just the temperatures of the individual components through a CSV file, we can get a particular lifetime prediction. So this gives us a sort of a lifetime here of 2.9 years where we fail with our 20% probability failure. So we're not meeting our target of 5 years, we're failing at 2.9. Then the middle option is if we look at what happens if we actually do a thermal map of those contours like we did on the previous slide. In this case here, we can actually extend the lifetime of 3.2 years. So we're actually getting, by adding that realistic temperature profile, we're actually getting a better prediction. So, in this case, we can actually still failing. We're not quite meeting our 5 years, but at least we're getting a slightly better performance by making a better prediction. And if we compare this to option 3, where we had no real input, we just said it goes between, the whole board was either at minimum temperature or maximum temperature. Everything was all the same. In this case here, we're actually getting a worse prediction, okay? And this is because everything's assumed at the same temperature, whereas, for example, if we look at the slide here, some of these main components are getting much hotter than the rest. And these components can typically handle the heat a little bit better. Maybe some of these other components at the outer edges, maybe they can't handle the heat. And so if we make the wrong assumption and we make them too hot, we're going to see them as failing where actually they normally wouldn't. So this is why it's really good to throw an extra level of detail to our analysis and make sure that we're representing what's actually going to be happening. Then when we look from the mechanical side, so some of you might be familiar with Ansys Mechanical. This is our sort of main or flagship, that's the word I was looking for, flagship structural solver. We could do any sort of structural analysis within mechanical, from standard static tests to full-on impact tests, dynamic testing, modal analysis, as we see some animations here. And for what many people don't know is, as much as we do these types of analyses in Sherlock, we can do basic modal, harmonic vibrations, impact tests, so on. Much of that is actually run by mechanical. It's actually using the mechanical solver in the background. So in that sense, we can actually trust the results that come from Sherlock. It's based on a sort of detailed, proper physics solver in the background. But sometimes we want to do a little bit more than just what Sherlock can offer. Sherlock is very much focused around the PCB and the components on the PCB, but sometimes there are other analyses where we need to include a little bit more detail. So these first tests here, so these are typical tests that we could do within Sherlock. So we can do a thermal mechanical analysis in Sherlock. We could do some shock and vibration. We could do an impact test, maybe not including the whole cover here as we see in the tumble test, but certainly we can define some sort of drop or impact on the board. But maybe we do need to include some other detail, like, for example, that the box and the tumble test. Or maybe we need to include some other types of physics. So maybe looking at some fatigue and fracture mechanics in some of the smaller components. Maybe we want to include effects of moisture and moisture ingress, and so on. So, this is why we would want to link it to something like Ansys Mechanical. And the workflow is relatively simple. If you're familiar with Ansys Workbench, this is where we link all of our different products together to create this much bigger, more detailed project workflow. So Sherlock would act as a preprocessor where we define our board and all the component properties and all of that. And then we can extract our 3D simulation model from that. But the nice thing about working in Workbench is now we can include other effects and other components. So for example, here, we have an enclosure that we want to include in the analysis because maybe the stiffness of the enclosure will affect the stiffness of the PCB. So now we bring that model in. And then we can include it here as part of our analysis. So we can run a modal, we can do random vibration, all of that, all including the actual enclosure itself. So that's something where we can add value by running with other mechanical products. And then we can also take this information back into Sherlock. So we can then still get the same reliability predictions that we would like to see from Sherlock, but now it includes all this detail of the casing, that, or at least it's seen through the different stiffness of the PCB, the changing stiffness that now gets translated into Sherlock, and then we can make our predictions from there. Okay, and then we can, again, more on the multiphysics side. So we can now, it's not just about a structural analysis or just a thermal. We can actually now include the effects of both. So we can do our electrothermal. So we can say, well, based on the heating and the operation of the board, where's our power loss within the board? How does that create an actual heating in the board itself? So we can iterate through that a few times. And then we can take that over into a mechanical stress analysis. So we can see how does the temperature distribution in the board actually create a thermal distortion or mechanical distortion in the board, and how does that then affect the deformation of the board. And we can really go down to all the levels. We can go right from PCB level down to even a little sub-modeling technique. So, when you look at the full scale, you get the general behavior of the board, but you're unlikely to capture all the details, for example, at the solder ball level, what's actually happening in the solder ball itself. So this is where we could use a technique called sub-modeling, where we actually take the deformation plot of the global model, the big PCB, and we can map that onto a much smaller model. So this is essentially a slice through of the PCB. We can see the solder balls, and maybe this is a slice through of the chip on top of the solder balls. And then we can actually look specifically at all the stresses and deformations through all those different layers. And we can get a really good mesh in that area to capture all that details. And that's something that we would never be able to, or would be very time consuming to do for the full board. So using a technique like sub-modeling is very appropriate for this and very useful. So this is where we can kind of bring in the strengths of mechanical. Mechanical has all the framework for the sub-modeling and thermal modeling and everything all together. So we can really then take our Sherlock analysis and take it a step further and get far more detail than we would be able to if we just stayed within Sherlock. Okay, so I kind of want to end off here with a little bit of just a little map of maybe how Sherlock can kind of fit into your organization. So we've kind of looked at kind of a basic project workflow, and we've separated out different users from the electrical simulation user to the thermal to mechanical and even Sherlock. But I mean, you're welcome to use multiple or single user for multiple levels. But you can see here that as we run through the project and we've actually sort of defining the board itself and defining the information of the board, we can already start using Sherlock as a pre-processor. So we start defining the board, start figuring out the layout. If we want to do some electrical simulation, well, to test the board. But then once we've kind of got a layout of the board, we can then use our thermal and our mechanical simulations that we see now to really interrogate the board design, make sure that it's going to last and it's going to do what we want. And then we can wrap up with our reliability predictions. And then we can, once we're happy with those reliability predictions, we can then go ahead and actually finalize and approve the design. So, again, this shouldn't be somewhere seen at the end of the project. The simulation should be seen as part of the workflow, working in tandem with the initial design, so that we can make better designs earlier on in the design process and not be caught off guard at the end. Okay, so maybe this can just serve as an idea of where Sherlock could be useful to you in your organization. All right. Thank you, everyone, for your time and for listening to the presentation. If there are any questions, I'll take them now.
Thanks so much, Evan, for the great presentation. I'm just quickly going to stop the recording.